Okay, so we're going to do a very important section to this course, which is section 3.2. We're going to talk about measures of variation. Before we talked about measures of center, so my data looks like this. In the middle is kind of the mean. Notice the data is relatively symmetric. And then the measures of variation say, how far out or how spread out is my data? How does my data vary from the mean? See, told you, single most important topic, so pay attention. The big one we're going to do today is standard deviation, which is linked to variance. Yeah, we'll round to one extra decimal place. No problem. I'm not too worried about your rounding. Okay, the range. Max data value minus minimum. Easy to find, but notice if either of these is way far away, you're really going to affect the range, so it's non-resistant. Outliers will affect it. And it doesn't take every value into account. We do it just to get a quick idea of how spread out the data is. I think you can do this. Pretty sure you can subtract. There you go, you got your range. Notice if this was 155, it's really going to change this. It affects it a lot. Okay, we got new letters here. S, that's your standard deviation from the sample. This is sigma. That's your population standard deviation. Just like with the mean, we had X bar for a sample, we had mu for the population. So we're using Greek letters for population. This is an ugly formula. I do not expect you to do this. I don't have you calculate it. I give you a website that does it. I just want you to show you these formulas so you'll be more appreciative of the website. This is it. The reason it's called deviation, it's how far do the data values deviate away from the mean. So if I had data like this, that's really tight together, and if I have data like this, which is really spread out, so if this is 1 and this is 2, your standard deviation for the data set 1 is going to be less than the standard deviation for data set 2. Units are the same as the original data value, so the units match the mean. But it's not resistant to outliers. So it's a biased estimator. We'll worry about that later when we're working with standard deviation and variance. We have to make sure of some criteria before we can do some tests. Okay. We're going to use this today, where basically it says that if you have a mean here and you go out 1 standard deviation, add 1, go out 2 standard deviations, add 2 of them, go the other way, subtract 1 standard deviation, subtract 2 standard deviations. That should be subtract. Saying that most of the data values fall in here. So out here, there would be 2.5%. Out here, 2.5%. So here's maybe a better picture. They're talking about the population. So if you're out here, remember that's the 2.5% above the standard deviation, that's significant. If you're here, if you're outside 2 standard deviations below the mean, 2.5% of the population, that's significantly low. Above and below. Here's a demonstration. This is Vern Troyer, Mini-Me. This is Yao Ming, the basketball player. Well, you can see that Yao Ming is an outlier or statistically significant on the upside. Up here, Yao Ming lives here because he's so tall, and Vern lives down here because he's shorter. You don't see a lot of either one of these walking around. This is a really rough estimate. So if you get some sample data, you can just take the range and divide by 4. And again, you get an estimate of the standard deviation. That way, at least you can tell maybe when you do the calculation and it's way far off, maybe you typed in a wrong data value. When you get to easycalculation.com and do this, you'll see that you get 2 calculations. So the population standard deviation uses all the members of the population. The sample, finding S, it doesn't use all the values in a sample. It's degrees of freedom. We don't dig that deep into the theory here. Variance is related to standard deviation. You just square it. So if my population, so suppose I had standard deviation of 12, my variance is that squared is 144. You can go the other way. Suppose I have a population variance of 121. Well, the population standard deviation is the square root, would be 11. So they're related. So here's all our notation. Now the variance is not resistant, but this is the big thing here. We can use the sample variance to target the population variance. It's unbiased. So we'll do that later on when we're doing hypothesis testing and such. Okay, I'm going to just show the picture here. Do this a lot. So this is our rule of thumb. Within 1 standard deviation, 68% of the population. Remember, within 2 standard deviations, there's 95. And then within 3 is almost all of our data. So what we care about is within this 2, because remember, outside here are significant values. Okay, IQ. Here's the picture that you're going to draw a lot in this class. We have a mean of 100. This is the population. So this is mu is 100, sigma is 15. So if I go out one standard deviation, this would be 115. If I go out one more, that's 130. Now, if I go the other way, if I subtract one standard deviation, that becomes 85. And then out here is 70. So the question is, they're asking what percentage of the population is between 70 and 130. That's between two standard deviations away from the mean, and that's 95%. So if I ask you, is an IQ equal to 138, is that unusual or significant? Well, you would say yes, because 138 lies above two standard deviations. Same thing if I said, how about an IQ equal to 60? You would say yes, because 60 is out here, which is more than two standard deviations below the mean. Chebyshev's theorem doesn't come up that much. Basically, it says if you're talking about two standard deviations away from the mean, you get 1 subtract 1 over 2 squared. It's 1 subtract 1/4. It's 3/4 is 75%. So that's any set of data. So if you do a sample, you can quickly say, okay, I know at least 75% of my data is within two standard deviations. Well, if I do that, 75% within two standard deviations, and that's my abbreviation, of the mean. That's what we just did. In the middle was 100. Two standard deviations above is 130. Below was 70. Chebyshev's theorem says at least 75% of any data set doing IQ would be between 70 and 130. It's more of a theoretical statement than practical. And that's it. In the next video, I'm going to do an example with real data that ties all of this together.